Good evening, everyone. Thank you for joining us for our Science Speaker Series, the final one of June 2023. It is such a pleasure this evening to welcome Dr. Giovanni Fazio from the Harvard-Smithsonian Center of Astrophysics. Dr. Fazio will share in his lecture with us. He will take us on a grand tour of the universe, beginning at our planet Earth, traveling through our solar system, galaxy, and into extragalactic space, ending at the edge of the known universe. We will enjoy this fascinating and exciting journey that Dr. Fazio will take us on this evening. I would like to share a special thank you to our major sponsor, Bank of America, for making our Science Speaker Series complimentary and accessible to all of our viewers and participants this evening, as well as a huge thank you to Cisco Brewers of Nantucket, as well as the White Elephant Hotels and Resorts. Before I hand it over to Dr. Fazio, a quick, brief bio on him, and nothing that I share will be suffice enough to summarize all of the amazing work that he has done over his long career. Dr. Giovanni Fazio is currently a senior physicist at the Center for Astrophysics at the Harvard-Smithsonian. He's faculty emeritus of the International Space University in Strasbourg, France, and for many years he has served as a lecturer in the Astronomy Department at Harvard University. He received his Ph.D. in physics from the Massachusetts Institute of Technology, MIT, and has performed research in the area of space astronomy for over 60 years. He has been the principal investigator for instruments on 3 space telescope missions and co-investigator on a 4th space mission. He was also the principal investigator for NASA's Spitzer space telescope infrared array camera, which observed the universe for more than 16 years. He has served on numerous NASA advisory committees and is the recipient of many national and international awards. Again, a very accomplished and distinguished career, and it is my sincere and utmost pleasure to welcome Dr. Giovanni Fazio to Murray Mitchell Association virtually this evening. Dr. Fazio, welcome, and thank you so much for joining us.
Thank you, Janelle, very much for that introduction. I'm so glad to be here and glad to have this opportunity to explain my research and what I do to everyone. Yeah, thank you very much.
So excited for you to share. Whenever you're ready, you can take over the screen and you can.
Okay, I'll share now.
Awesome.
Okay. Very good. Can you see that okay? Everything? Yeah, right.
Yes.
Okay, great. Okay, I want to thank everyone for coming, and I'll try to make this as enjoyable as I can. It's really a very exciting journey, and I hope you'll enjoy it. So let's go to the first slide. This is a picture of the Earth. It's so-called the blue planet, and it's blue mainly because 70% of the planet is water. This photo was taken by the Apollo astronauts on their return from the Earth, and I think this picture is one of the greatest achievements of the last century. And the reason I say that is, you know, this Earth is really just a spaceship, and we're all astronauts on this spaceship. When you look at this picture, you don't see lines between countries or anything. We're all just one people on this spaceship, and I think we had better learn to take care of it. One of the things I want to emphasize is that the atmosphere on Earth is very, very thin. And this is a picture of the edge of the Earth taken from the International Space Station, and you notice it's only 100 kilometers in thickness compared to the diameter of the radius of the Earth, which is 6,400 kilometers. So it's only about 1.6%. It's not a sharp cutoff, but 100 kilometers is about a quarter of the Earth's atmosphere. But it just shows you how thin and how fragile it is. And again, another warning that we have to be very, very careful taking care of it. Now, the Earth is a planet that goes around the sun. This is a picture of our sun. The sun is 110 times the diameter of the Earth. And it's very interesting that in the survey taken in 2012, when people ask whether the sun goes around the Earth or the Earth goes around the sun, 26% said that the sun goes around the Earth. So I think we astronomers have some education to do. Okay, the sun is a star. It's basically a ball of very hot gas, mostly hydrogen helium, that's completely ionized. And then the heat generated by the sun comes from nuclear fusion at its core. That is, it's the same principle that of the hydrogen bomb. Protons and neutrons collide basically at very high temperatures and turn into helium or alpha particles. And the extra energy generated by that way pushes thermally, wants to expand this gas, but gravity collapses it. And the sun then is in this thermal equilibrium between gravity and the thermal outward pressure. Now, the sun burns something like 700 million tons of hydrogen per second. And at its center is it's 27 million degrees Fahrenheit. But the surface is only at about 10,000 degrees Fahrenheit. Then the sun has an atmosphere called the corona, which is also a very tenuous plasma. And that temperature of the corona goes from 1.7 million Fahrenheit up to 17 million. And we don't know how that gets so heated, so hot compared to the surface, which, remember, I said it was about 10,000 degrees. So that's still a mystery. In 2.5 billion years, the sun will lose all its fuel at its center and will start to expand and engulf the Earth essentially and burn it up. So this is a picture of a coronal mass ejection from the sun. These are bursts of plasma, of high energy particles, protons, electrons, and primarily that are thrown out from the sun and can have serious impact when they collide with the sun, with the Earth. I'll show you. This is another picture of a very active sun. This was a composite image taken from 2 instruments on the SOHO spacecraft. So this solar wind comes off at very high velocities, 671,000 to 1.8 million miles per hour, and very high speed. And when these particles essentially hit the Earth, it causes the aurora, the northern and southern lights. And it can also cause damage to satellites in high Earth orbit, like the GPS, the communications, weather satellites. And it can also induce currents in transmission line, blow transformers, and generate blackouts. There was an immense large one in 1859 called the Carrington event, and in 1989, Quebec had a complete blackout due to these coronal mass ejections. So surrounding the solar system are 8 planets. I said 8 instead of 9. Pluto has been demoted to a dwarf planet. I'll come back to that in a minute. So the top part shows the inner solar system: Mercury, Venus, Earth, and Mars. And these are the so-called rocky planets. Then we have in the lower level, Jupiter and Saturn, which are gaseous planets. They have no hard surface. And then Uranus and Neptune are the icy planets. Then the elevated or large orbits that you see in the bottom panel are that from the dwarf planets, or sometimes called the Kuiper belt planets, that are outside the solar system. So like Pluto, Eris, Haumea, Makemake. One of the things I wanted to mention to you is the origin of the Earth's seasons. Many people think that during the summertime, the Earth is closer to the sun and at winter far away. But the truth is, it's just the opposite. Actually, the Earth is closer by a small amount to the sun during the winter and further away during the summer. The seasons are really due to the fact that the Earth's axis is tilted by 23.4 degrees. As you can see here, that causes in the diagram below there, which is the scene in the low density of the incident solar rays in the northern hemisphere and the high density of incident rays in the summer. And so it's this tilt in the Earth that really causes the seasons of the Earth. Now, one thing we have to do as we go further and further, I can't use miles or kilometers anymore. I'm going to, let's see. I can advance my. Oh. Okay, can you still?
Yes, we can see the origin
Okay.
of the season.
Yeah, I don't know why. Okay. Okay, there you go. Sorry about that.
No worries.
Okay, so let's discuss. We have to use new distances to measure distances in the universe. The first one is the astronomical unit, sometimes called AU. It's the mean distance between the Earth and the Sun. It's about 150 million kilometers or 92 million miles away. Another unit is the light year. This is the distance traveled by light in 1 year, which is 9.46 times 10 to the 12 kilometers, or 5.7 times 10 to the 12 miles. Now, to get an idea of how fast the light is, if in 1 second, light can travel around the equator of the Earth 7.5 times. So you see the speed of light. Okay, so these two units, astronomical unit and the light year. Another quantity that's useful is that 1 light year equals 63,000 astronomical units. Okay. So let's look at the solar system now. So the distance from the sun to the Earth is 1 astronomical unit. And interesting, it takes light 8 minutes to go from the sun to the Earth. So it's interesting that when you look at the sun, you're always looking at the sun the way it was 8 minutes ago due to this light travel time. The distance from the sun to Pluto is about 6 billion kilometers or 40 astronomical units. And the light there takes 5.5 light hours. So it's interesting, when recently we sent a satellite, the New Horizons, to take a picture of Pluto, this light signal out there took 5.5 and another 5.5 back. So once you sent the signal, you didn't get a reply for 11 hours later. It's very difficult to communicate out there. This is a picture then of all the planets in their relative sizes and everything. And here you can see the size of Jupiter and Saturn compared to Uranus and Neptune, and Pluto is a little dot there. Pluto is actually smaller than the size of our moon. It's about 2/3 the size. Okay, here's another view of our relative planet. I like this picture because it shows the more in detail the relative importance of the sizes. Here's the Earth and Venus, Mars, Mercury, and Pluto. And here is Jupiter and Saturn, Uranus and Neptune. And you can see Earth, Mars, Venus, and Mercury, and little Pluto. And here's the sun compared to the Earth. Remember the diameter of the sun is 110 times the diameter of the Earth. It's really quite large compared to the planets. It's interesting to see this view. It puts it more in perspective. Okay, now this is start looking a little bit further out into the solar system. One important thing to note is in the upper left panel that between the orbits of Mars and Jupiter, there is what we call the asteroid belt. It's a belt of rocky objects called asteroids, and we'll come back to this again in more detail. These are bodies that never really coagulated together to form another planet in that region. Now, if you go to the upper right corner, and there you see the box on the left is the little square in the center now, and you can see Saturn, Uranus, Neptune, and Pluto's orbit. Another thing you notice that Pluto is really sometimes comes on the inside of Neptune and is highly tilted also. And then if you go to the lower right corner, you can see some of the orbits of the Kuiper belt are dwarf planet objects with respect to the solar system. They can be very large. And then if you go to the lower left side, that square on the right is now the little box in the center. And on the outside of this blue ring around there is called the Oort belt. We think there's a reservoir of comets out there. We have never detected the comets out there, but we know that some of them have collisions and then come into the Earth, in the region of the Earth, across the Earth's orbit. And from those orbits, we know that there must be a reservoir somewhere out there, but we know very little about that Oort cloud. We'll come back to in more detail to all of this. Okay, so this shows a picture of the asteroid belt in more detail. We think there's as many as 700,000 to 1.7 million of these objects. And occasionally, some of these objects can have a collision and change their orbits so that they come in and orbit around the sun and then go back out again. And the ones that cross the Earth's orbit are called near-Earth objects, and there may be about 20,000 of them. And if one ever hits the Earth, it could cause a serious damage. Also, you see around the orbit of Jupiter, the so-called Trojan and Greek asteroids in Jupiter's orbit. They're at plus or minus 60 degrees from Jupiter. And there's a stable point there where these asteroids can collect. These are some pictures, actual pictures of some of the asteroids. The largest one can get like 400 miles in size. And the four largest asteroids are already about 1/2 the mass of the whole belt. The largest one in their series is always already classified as a dwarf planet. It's about 550 miles in diameter. And that's a worry for us and our planet. I mean, there's evidence already that some of these objects have, impacted the Earth. The famous one involved with the extinction of the dinosaurs that hit in the Yucatan Peninsula. That one was about 10 to 15 kilometers, or 6 to 9 miles in size. So there's a continual lookout for any of these, and and also trying to figure out what to do if we saw one coming. There has been evidence lately in the attempts to practice what we would do. And one recent satellite went up and fired a trajectile at the test asteroid, and noticed how much we could change their orbit. And it appears that method might be successful. The problem is in knowing when they come, particularly the ones that come from the direction of the sun, are very difficult to detect. These are the dwarf planets as we know them now. Sedna, Aurora, Pluto. And then just to compare it to the Earth and the Moon, you see Pluto is actually smaller than the Moon. Now these planets are at 30 to 100 astronomical units away on the outside. And what these objects are, they're essentially remnants. When the sun was formed, it formed by the collapse of a molecular cloud of gas and dust. But the collapse occurred into a disk around the sun, and then that dust eventually coagulated in what we know as planets, and this is sort of the debris on the outside of that dust disk. So they're really the remnants of the early formation of the solar system. There's 2,000 known now. Kuiper Belt or dwarf planets out there, and there may be as many as 70,000 out there. This is a picture of Pluto taken by the New Horizons mission just recently in 2015. It's the last planet to be, well, now a dwarf planet it's to be photographed in the solar system. It's very interesting. It's mainly an icy type object. Now, Pluto, as I mentioned before, was demoted basically from a planet to a dwarf planet. And there was quite a bit of controversy when this happened, not even among astronomers, whether it should have been devoted or not. And a lot of newspapers picked this up, as you can see here, in that size doesn't matter, protest for Pluto, plutonic love, planet killers, how would it make you feel? But there's still some controversy over whether this should have been done or not. But it caused the International Astronomical Unit to define what a planet is. And the definition now being used is a three-part one. It's first, has to be in orbit around the sun. Second, it has sufficient mass to be circular in size. That is, it's nearly round. And third, it has cleared its neighborhood around the orbit. And that is, it's not a satellite of another object or anything. So according to that definition, Pluto didn't make it and was demoted. Now, this is going a little bit further out now. We have the upper picture in the blue box there shows the Pluto's orbit. And there you can see the orbit of a binary Kuiper Belt object and the relative location with respect to the solar system out there. Then on the outside of the Kuiper Belt objects is this Oort cloud that I mentioned earlier, which I think is a large reservoir of comets out there. It's about a light year in size. And there may be billions of comets out there. We think that from the sun to the Kuiper belt is of the order of 30 to 100 astronomical units. The Oort cloud is greater than 10,000 astronomical units, or about a sixth of a light year. And it could go out to as much as a light year, as mentioned there. So we have yet to detect this, but this is our best idea, a theoretical idea to explain the comets that we see about the nature of the Oort belt. Now I want to divert just a little bit second, because we have an interesting object that has entered the solar system. We have an object, we had the first evidence of an asteroid coming from outside the solar system recently. This was in 2017, this happened. And the reason we know it was from outside the solar system was because of its velocity and because of its orbit, which is a hyperbolic orbit and highly inclined. So it wasn't from our own solar system. And when looking at the light curve, the light intensity as we're tracking it, it varied by a factor of 10 to 1. So it was either an elong object, as the artist illustrated on the left, or a very flat type object, as illustrated on the right. The name given to this object was Oumuamua. It was because which is Hawaiian for a messenger from afar. And the reason it was Hawaiian, because the telescope that discovered it, the Pan-STARRS telescope, was located on the island of Hawaii. You notice it's very dark and reddish, similar to systems in the Kuiper belt. We think it's about 1,000 feet long, maybe, and but this 10 to 1 ratio really caused. Normally, we don't know of an asteroid with that sort of dimensions on it, so immediately stirred feelings that this may be a spacecraft from another planet system, and so the activity started on this. The speed that it came in with was about 87,500 miles an hour, very, very fast. So radio astronomers looked at it and didn't find any emission from it or anything. So, and it's another odd thing about it was that it was seen to be accelerating, which is unusual, because it had no tail or anything located behind it, and but I think the conventional thinking is that just another object that came in from another solar system, and but no, it's not an alien spacecraft or anything like this. But it did generate an interesting idea that, instead of looking for civilizations by listening to radio waves or by looking for laser beams beamed to us from another civilization, perhaps maybe we should be looking for the remnants of other civilization. Professor Avi Loeb at Harvard has been a strong proponent of this idea. That the main idea is we should be looking for these remnants that from another civilization that might be entering into our solar system. We expect about 10 of these asteroids be coming into our solar system per year, but they're very difficult to detect. Soon we'll have large ground-based telescopes that will be scanning the whole sky every few nights, and these will certainly be in a position to start detecting more of these. Okay, so this is a movie I'm going to show now summarizing what our solar system looks like. They're the inner planets. the asteroid belt, the outer planets, Pluto orbit. Then you see the Kuiper belt objects. And then finally the Oort cloud. Okay, then nice summary of what we saw. Okay, so let's go on now. Let's see. Well, one other thing I want to bring up is very interesting. Is there a planet 9? Is there another planet out there beyond Neptune? And there's always been a lot of speculation about whether one is out there. But recently, by looking at the Kuiper belt objects, as are shown here, this unusual arrangement of these orbits suggested to people that this happened because of a planet 9 perturbing the orbits. And one could then predict where this planet 9 orbits. The prediction was it would be 400 to 800 astronomical units, and maybe would be 5 to 10 times the mass of the Earth, and would have maybe an inclination to the plane of the solar system of about 15 to 25 degrees. Well, it's been for years now since this was proposed. People have been looking for it and have not found it, and there's no evidence of it, but it still comes up every once in a while, and people, I think, are still looking. Although there's, thus far, after many years of looking, there's no evidence at all that such a planet exists out there. Okay, so let's go on now outside our solar system. See in this diagram, you see the sun, then the Oort cloud, 2 light years out, 4 light years out, we come to the first star. It's a triple system called Alpha Centauri. It's Alpha Centauri A, B, and Proxima Centauri. Let's go to the next one again. Proxima Centauri is the nearest star, 4.3 light years away. It's a small red M dwarf star, and it has evidence of a planet around it now. I'll come back to that. Within 17 light years of the sun, we know about 65 stars similar to our sun. And so the distance from the sun to Proxima Centauri is about 6,000 times the size of our solar system. The Proxima Centauri system there is 3 stars. I mentioned A, B, and Proxima Centauri. And Proxima Centauri is the closest one. One of the problems, the mere fact that this is the closest star and there's a Earth-sized planet around it, caused also a lot of interest among astronomers. But one of the problems with Proxima Centauri is that being a small M dwarf star, it flares quite a bit with ultraviolet and X radiation, and would get rid of the atmosphere and make life very dangerous if you were living on the planet nearby it. So, it's interesting that the question arises then, well, can we ever reach Proxima Centauri? Can we ever get there? Well, if you try to take a spacecraft, as we know now, using chemical rockets, they travel at about 12 kilometers a second or 26,000 miles per hour. And it would take 100,000 years to reach there. So if you wanted to go, say try to reach there in 20 years, you have to travel maybe about 1/4 of the velocity of light to get there. The immediate impression is that it may be impossible to get there. However, there is a program now called Breakthrough Starshot, which proposes to send a collection of small satellites the size of an iPhone sample. And what you do is accelerate them with a phased array of high-powered lasers to accelerate them. And this way you could get them up to a high enough velocity. And this program has received from a private investor $100 million to develop this thing. You'd have to accelerate these up to about 100 million miles per hour. So it's an interesting idea, but quite a bit of effort has to go into this to make it anywhere realistic. Okay, let's look at go out now a little bit beyond and look at the stars. You can see stars come in all sizes. Most of the stars in our galaxy are smaller than the sun, about 2/10 of a mass of the sun. The largest ones are like Betelgeuse and Antares, which are called red supergiant stars. They have a radius about 1,000 times the sun, and are bright 100,000 times brighter than the sun. Here you can see the sizes relative to other stars and to the sun. And, right, okay. Mainly the object of this was just to show you that there's a large variety in solar stars and in luminosity. Okay, as we go further out into the solar system, we see that the space between the stars is not empty. It's filled with gas and dust in the particles. This is a picture from the Hubble Space Telescope showing what are called the elephant trunks in the Eagle Nebula. The size of these structures are a few light years, and some of these can get up to 50 to 300 light years in size. And typically, even inside these clouds, or the density inside is even lower than anything we can get here on Earth. There's only about 100 to 1,000 atoms per cubic centimeter in there. And outside these clouds, there's maybe one hydrogen atom for 4 cubic meters of space. But and it is these objects. So the main point I want to make here is that between the stars is a low vacuum, obviously, but not completely empty. It is filled with this gas and dust, and it is in these large clouds that part of them can start to collapse, and this is where planets and stars are being formed in these molecular clouds. Let me just show you a little bit about what the dust is in here. These are very small particles, less than a 40 millionth of an inch in size. This distance to get it's hard to get it. Almost this is the other extreme of going to astronomical distances. You're down in the smaller range, but this is about these particles are about 100th to 10,000th the thickness of a strand of hair, so they're incredibly small. And one dust particle exists in almost every million cubic meters, but the total mass is only 1% of the interstellar medium, or in these dust clouds. And what do they consist of? Mainly long, dirty ice grains, grains of graphite, which is carbon, silicate particles, which is like sand, and particles with small cores and ice around them. And some of them are large, complex molecules, and also can be some iron particles too. So these molecular clouds are primarily gas and dust, 1% dust. The rest of the gases are mainly hydrogen and helium. Okay, let's go on out further now. So what we find is that the stars that we see in the sky are clustered into vast stellar associations in the shape of thin disks called galaxies, which are the basic building blocks of the universe. A galaxy is basically an island of stars. At night, we see our galaxy as the so-called Milky Way, and our galaxy contains about 200 to 400 billion stars. Now, we can't get a picture of our galaxy, but this is what if we could get outside our galaxy, this is what it would look like. Approximately 100,000 light years across, and as I mentioned, containing maybe 200 billion stars. It's about 1,000 light years thick. So it's almost like a CD, right? Very large in diameter, but very, very thin. Now, our sun is about 2/3 of the way out. And we're located here, and then gradually going around this, rotating with this disk of stars. It takes us about 200 million years to go around once in this. It's interesting to note that the speed, if you're on the equator of the Earth, you're traveling at about 1,000 miles per hour. And then the Earth is going around the sun at 67,900 miles per hour. And then the sun is going around the galaxy at 448,000 miles per hour. Like I mentioned earlier, it takes about 200 million years to go around. Also, it's interesting to note that the solar system is tilted about 60 degrees to this plane, in galactic plane here. So the solar system is not a plane in there, so it's tilted about 60 degrees. And also at the center of our Milky Way galaxy is a massive black hole that contains 4 million times the mass of the sun at its center. The next diagram shows an artist's drawing of what we think our galaxy looks like. The face-on drawing of the Milky Way galaxy. See this barred structure in the center. And this was drawn from radio, infrared, and visible data. It's a 2-armed barred spiral, several secondary arms coming out. You can see our sun is located in what is called the local arm there. So this is what we think it looks like. Now, since we live in this disk, when we look at it, we just see this thin disk. And if you're in a very dark place, you can actually see the disk of stars. And this is a picture of that disk. The dark parts are due to dust in the interstellar medium in the galaxy. You have to be in a very dark site to see this. But if you look at infrared and take a picture of a galaxy, infrared radiation can penetrate the dust, and then we see it as in its true form here, which you can see. It's sort of this square box type material in the center here. This is all stars, and Emeritus do the stars. But you see how thin it is compared to its size. Okay, let's keep going on out now. And pretty soon, our nearby galaxy is the Large Magellanic Clouds. They're about 163,000 light years from the sun. This one is about 14,000 light years in diameter. It only has about 1/100th of the mass of the Milky Way. But it can be seen by the naked eye, but you have to be in the southern hemisphere to do it. And there's another galaxy nearby called Small Magellanic Cloud, 206,000 light years from the Earth. And again, you can see this with the naked eye, but you have to be in the southern hemisphere. This is the various type of galaxies that exist in the universe, elliptical size, and a sub number depending on the ellipticity of the object, and spiral galaxies depending on how tightly the arms are wound, and barred spirals with the bar at the center, and irregular galaxies like the two galaxies I just showed you, the Small and Large Magellanic Cloud. It's just to let you know that there are these various types. And here are some various pictures of them. The two up in the upper left are showing two galaxies about to collide. And the upper right is a collision that has occurred in the past. Down below in the lower right, you see a grand spiral galaxy. And the right, an elliptical galaxy with a dust ring around the center there. So there's all kinds of galaxies. Okay. The nearest nearby galaxy to us, one of the largest ones is we'll call Andromeda. It's called Andromeda Nebula because it looks that way when you look at it with your naked eye. But it is a nearby galaxy that looks very much similar to our galaxy. And it's about 2.5 million light years away from us. It's a barred spiral type galaxy. And when you see this, it's interesting that this galaxy is approaching our Milky Way galaxy. And it will collide with the Milky Way in about 4 billion years, and expecting it to collide with it. It'll essentially pass right through our galaxy and disturb the stars, but there's so much space between the stars that the effects are primarily from the distortion, gravitational distortion of the two. This galaxy is about 220,000 light years in diameter, and it also can be seen with the naked eye. So now what we next notice that just like the stars accumulated together to form a galaxy, essentially an island of stars, we notice that the galaxies around us began to cluster in a similar manner. That is, galaxies define the large-scale structure of the universe, and they tend to be clustered. That is, they're not distributed randomly. The clustering ranges from a few pairs to loose groups to giant rich clusters. Our local group contains about 50 galaxies, but there's some clusters that contain well over 1,000 galaxies. And clusters are about 100 times the size of our own galaxy. So this is, you're beginning to see some of the order that is really in the universe in these clusters. And here's an example, a drawing of what our local group of galaxies look like. So this size is about 5 million light years in diameter. This is another picture of the Virgo cluster of galaxies, which is about 59 million light years away, and there's about 2,000 galaxies in that cluster. Here's another one called Abel 1689. You can see the clustering. Another interesting thing is if you look at the edge of this galaxy, you see these streaks over here. Have the marker up in the upper left. See these streaks here. What happens is that these clusters of galaxies can act like a lens for an object behind them. That is, light, as it travels through the cluster, gets bent, and the cluster can act as a lens, basically, and magnify what an object behind them looks like. And a lot is being made of this to study very distant galaxies and everything. But you see a lot of these arcs in here, and also, that's always due to this gravitational, it's called gravitational lensing, the bending of light as it goes through a very dense cluster of galaxies. And here shows the distribution of nearby clusters of galaxies. Each one of these names is a cluster of galaxies. And what you can begin to see now is that just like the galaxies clustered, the clusters of galaxies cluster. You follow this, right? So now we're going to see supercluster essentially forming. This supercluster here is the order of 300 billion light years in size. So clusters of galaxies can form superclusters. It's more than 100 clusters in the supercluster. And our local group of galaxies is a member of the Virgo supercluster. And the size of a supercluster is about 20 to 30 times the size of a cluster of galaxies, or about 300 million light years in size. So there's this beautiful order in the system. The stars cluster to form a galaxy. The galaxies form local groups, and then clusters of galaxies, and the clusters bound together and form superclusters till you get on size to the size of the universe. This is a radio map of superclusters of galaxies in the universe. You can see the right. One thing you notice here is just 1 second here. You notice is that the galaxies are not, and even these superclusters are not distributed uniformly always. They seem to form into these strings and surfaces and walls and everything, which is a very interesting structure. So the large square structure of the universe consists of these strings of superclusters, that sometimes look like walls, and these large areas where there's nothing, essentially looks like there's nothing, the voids. And the walls are the largest structures that we've ever observed. And totally there are approximately 200 billion galaxies that we know of in the universe. And each one of those galaxies contains at least maybe 200 to 400 billion stars. This is a theorist simulation of what the large-scale structure of the universe may look like. Again, you can see the voids and the strings. I like to compare it maybe to a bowl of soap bubbles. You can imagine that. So the universe structure is more like a bowl of soap bubbles than it is. The galaxies are not uniformly distributed. through the universe. On small scales, on a large scale, there is uniformity. Here's another. This is a theoretical simulation of what it might look like. And the galaxies along these streams, an intersection of the streamers cause these bright superclusters to form. Here you can see one of those blown up into showing you what a supercluster might look like. This is the deepest image of the universe taken thus far, recently by the James Webb Space Telescope. This is a very small region of the sky. In fact, if you hold a grain of sand at your arm's length, this is how much of the sky this picture would cover. And every dot you see in there, except for that bright one with the spokes, is a galaxy. So you can see how dense this gets in a fascinating picture. And the deepest objects we've seen thus far. When you look deep into space, you're looking back in time because of the length travel time that it takes to reach us. So some of these galaxies, the little red dots in there, were made perhaps maybe only 400 million years after the Big Bang. So we're continually trying to look deeper and deeper and go back further and further as we approach the beginning of the Big Bang. Another thing is the cosmological principle. That is, on a large scale, the universe is homogeneous. This is very interesting. That is, the universe looks the same at all distances that you go. Not on the small scale, but on the large scale. No matter which direction you look, it looks the same. And that's what is called isotropic. That is, the universe looks the same in all directions. So these are two basic principles. The universe is isotropic and it's homogeneous. And it didn't have to be that way, but that's the way it is. So this is a summary now of what we've just gone through. We have the solar system, which is 40 times the distance from the sun to the earth. Then we have the nearest star, which is about 6,000 times the size of the solar system. Then we have our galaxy, which is 25,000 times the distance from the sun to the nearest star. And then the local group, which is 10 times the size of our galaxy. We have clusters of galaxy, which are about 100 times our galaxy. Superclusters, which are about 20 to 30 times the clusters of galaxies. And these walls and voids, longer streams, and that are 300 times the cluster of galaxies. So you see, each time we step up, we go likely by a factor of 10 or so. So it's really quite fascinating. The structure of the universe is really fascinating. I just want to close with this statement: what a beautiful and amazing universe we live in. But before I give up and go to questions, let me leave with you two ideas. When you see all of this, the immediate impression is, wow, we are nothing. We are zero in the universe, right? Well, don't get depressed, because with the few kilograms of matter in our brain, we were able to look and see what the universe looks like. Well, think about that. We were able to determine what the universe looked like, and that's rather amazing. And the second point I want to bring to your attention is, it's not a chaotic system. There's incredible order and beauty in this whole system. It just wasn't random distribution. There's just tremendous amount of order. And Lord knows we have much more to learn about the universe. So I'll finish there and hope you enjoyed this. Okay, thank you. Okay.
Thank you so much, Dr. Fazio. What a breathtaking and amazing journey through our universe and through the extra galaxy. Can you share with us some of the order that has been observed about our universe? Can you speak to that?
Yes, well, I just went through that. The last slide here, I think, explains most of it. Yeah, like I said, you know, all the stars form into galaxies. Galaxies is sort of the basic unit of the universe, and I like to look upon a galaxy as an island of stars in the universe, and then the galaxies we find cluster into larger galaxies. That is, they're not uniformly distributed, and then those clusters are then cluster just like the clusters did. If I get all this straight, and then the clusters of galaxies form superclusters, you know, walls and void like that. Finally, you get these pictures that I showed you that are theoretical simulations showing this bubble-like soap bubbles in a jar, in a dish or some kind of structure in the universe. Yeah.
And audience members, please feel free to pop any questions you may have or any comments even in the Q&A section of the Zoom. And we have a question from Eric Olson. What did you learn or surprised you from seeing the oldest structures in the universe from the Webb Space Telescope?
Oh, yes. Yeah, that's very interesting. Yeah, some of my research is involved in this. Yeah, like I said, the deeper we look into the universe, and the James Webb Space Telescope made it possible for us to look deeper than we ever have before. It's a 6.5 meter mirror. When I worked on the Spitzer Space Telescope, that was only a 0.85 meter mirror. So James Webb is a big advance, and James Webb has been able to look deeper than Spitzer has into the universe. So we're looking back now in time about to maybe 300 to 400 million years after the Big Bang. And one of the interesting things that we're finding is we thought that it would take at least 1 billion years to form a galaxies after the Big Bang. But we're finding these well-ordered systems, sometimes some of them with old stars in them, at 300 and 400 million years. So there's a quandary here of how did they form so fast and so big? And that is one of the prime areas of research right now, looking deeper and trying to find out what's going on.
Amazing. What surprised you the most, you would say?
Well, I think that we found these, yeah, that we found, and there appears to be many of them, and also I think the mere fact that some of them look like they're old already, you know, and so how can you have an old galaxy at that stage of the universe? So there's something we don't understand about how these formed and how fast they formed and everything. And so a large effort is going into this to better understand it.
Amazing. Question from Stephen Chase. Do you think there is life beyond the Earth?
Ah, interesting question. What I didn't mention is that we now know that we now know more than 5,000 exoplanets, that is, planets around other stars. We know about 5,000, more than 5,000 right now. So it appears that every star probably has a planet around it. Now, I remember I told you there are 200 billion of these stars in our own galaxy. And maybe 10 or 20%, something, I don't know, 10% of these stars, of these planets may be Earth-like. That is, you'd want a planet what is called in the Goldilocks zone. It's not too hot and not too cold. That is, you want to get it from the right distance from its star so that ice doesn't freeze I mean, that water doesn't freeze or doesn't evaporate. And so it has to be there if you want to consider water as a vital component of life. And so a lot of effort now is going into finding these Earth-sized planets and then looking at their atmospheres with the James Webb Space Telescope to see if we can see the components of maybe biological components or evidence of life like oxygen, organic molecules, carbon dioxide, phosphine, and things like this. So there's a lot of effort going on. So you would think that with that there's billions, there might be billions of stars similar to Earth or habitable planets that exist even within our own object. And but to date, we have no evidence beyond Earth that there's any evidence of life elsewhere other than Earth, and people are still looking at it, looking for it. But the other thing is, we're a relatively young star in the universe. Earth is only 4.5 billion years old. The universe is 13.8 billion years old. So there was a lot of stars that formed before the Earth ever came into existence. And if there's stars and other civilizations around these stars, they would have been much more advanced in this space. And they, you would think that, looking within the 70 years of space, we've had 5 of our satellites go heading out toward beyond the solar system. So you can imagine our galaxy should have been populated by these civilizations. But as Enrico Fermi once called, and it's called the Fermi paradox, where are they? We actually know, we've looked for evidence of radio signals, we've looked for laser signals, nothing, absolutely nothing. That's why Professor Loeb is saying, well, maybe we should look for the remnants of these civilizations.
Right.
So that's the dilemma we're facing right now. I definitely think that we should look for them. I'm a strong believer in that. Whether they're out there or not, I don't know. It's hard to say.
I think that's a pretty scientifically neutral answer.
Yeah.
Second question, or rather third question, what is the current scientific best guess as to the likelihood of both life and intelligent life on other planets? Kind of a follow-up.
Yeah, that's right. It's thus far we just don't know. Let me also say there's, before we discovered these exoplanets, we thought we found another planetary system that looked just like the Earth's. I mean, it just looked like our own solar system. But none of them, other solar systems that we've found look like ours, right? So again, we have to consider this. These are completely different now. Whether intelligent life can develop on this is I just don't know. The best thing we can do is look for, once we find these exoplanets, to look at their atmospheres and try to determine whether there's biological molecules on there that we know, carbon dioxide, water, phosphorus, etc., that would be evidence that some life existed. But it's not simple to develop where we have developed right now. Like I said, I just don't know. But I'm a strong believer. We got to look hard. We got to keep looking.
And like you mentioned, maybe we need to look in a different angle at the remnants.
Yeah, that's an interesting. I thought, we've mainly been looking for radio signals. That's been the longest look, looking for coded signals that come to us. And over, I don't know, 20, 30 years, maybe longer, there's found nothing. Another technique is to look for, well, they would have concentrated there. If they knew about us, would they have contacted us? Or, would they have aimed a laser beam at us or something?
Mhm.
And people have looked for laser beam also, and found nothing. But there should be advanced civilizations out there because, like I said, their stars are far and way below before we got here.
Mhm.
And they should have populated they would have populated the universe either with their own starships or remnants of their civilization. We should have found something from them, and nothing that showed up. But we should keep looking. I think what
Yes.
somebody once said to me, well, the question is, but look at how much of the possible space have we looked at with the radio waves? And somebody mentioned to me, it's like going to the ocean and taking a cup of water out and then trying to say what the ocean looked like, So,
Right.
so we have to figure that we've only sort of begun to really do this search, and we can't conclude that because we didn't find anything, there's nothing out there. That's wrong.
Right.
There's still a possibility there's an intelligent life out there.
Thank you for that. We have a couple of questions from Patricia first, or rather comments and questions. First, thank you so much for this. Astrophysics is a personal, incredible interest of mine. First, which criteria of the three needed remove Pluto as a planet? We'll lead with that. That was actually one of my questions. I love that Patricia asked it.
Oh yeah. Let me see. Well, one of it is the. Let's see, that's an interesting question. Let me let's look at my notes to see where. Review those three again.
I believe one was that it had to be circular.
That's right. That's right. It's not. Yeah, that's one thing that it's not. It's an elliptical orbit, and it's alone in its orbit. And the third one was they cleared everything else out from its orbit, I guess. Yeah. So I think it's the orbit is highly inclined. In fact, it even comes within Neptune. Uranus, Neptune. It comes within Neptune. It's highly inclined, and those were the main. That was, I think, one of the main things. And also its size, but the size is not mentioned in the criterion. But I think it's the highly inclined orbit, elliptical type orbit.
But they got disqualified rather for their
Yeah,
elliptical.
yeah. So, there's still a debate going on, so
right,
as to whether it should be dropped.
Is it like a 50-50 split, or we split 60-40? What's the?
Oh yeah, I don't know what there was a vote of the International Astronomical Union, and I don't know how that came out. Yeah.
I might have to pull the community.
Yeah.
And Patricia's second question, based on Einstein's theory of increasing gravity slowing time, 24 hours on Earth is like 10 hours on Saturn. So in theory, if we could increase Earth's gravity, even in small bubbles like around a city, we could slow time progression in that city, slowing disease. Your thoughts?
Oh, wow. That's interesting. Now, let me say, we have seen a little bit of this, and if you, there have been masers that have been put in rockets and orbited around the Earth, and they show the effect of time on gravity. Yeah, it has been demonstrated now that lower gravity slows time. Yeah, so yeah, I have to think about that city. That's an interesting one. I've never heard before. I have to think about that one. Yeah. But as you get away, it does slow, but it's minuscule. And I think the proposed one would also be the amount of change would be very small.
And Patricia also wants to know, do you feel as though time is a human construct? What are your thoughts on time being a human construct?
Oh, exactly what time is to me is a mystery. I'm not quite sure. Because the minute you say now, it's not now anymore. right? So just exactly what is time? It's a means of indicating events, but books have been written on what is time, and so let me just say it is a mystery, and it bothers me quite a bit sometimes when I try to understand it. You know?
Maybe our work is to not understand time,
Well,
detach from it.
like I said, there's whole books written on it. Yeah.
Yeah. Eric Olson asks, what's your best guess for what was before the Big Bang?
Oh, we just don't know. We can't know, right? I mean, the laws of when you go back in time, the laws of physics break down before you get to the Big Bang,
Mhm.
and so we just can't know what happened what before then. It's pure speculation. What existed, what caused it to start? I mean, it's pure speculation. We can't know. And like I say, if you use the laws of physics, it won't exist.
Where exactly do the laws of physics start to deconstruct?
Very, very, yeah. Obviously, I don't have the exact number right now. We're very close to the Big Bang. Yeah.
Mhm. Right. I guess one question I have for you is what largely influences the shape of a galaxy? And forgive me if I missed you mentioning that.
Yeah. No. No. Yeah. When these form, we still don't fully understand how the galaxies form, but when they have a group of stars like this and it become over dense, they will essentially collapse on themselves due to gravity. But they don't come in and form a ball due to the fact they were probably rotating. Is they come in and form a disk. The same thing happens with stars. When gas and dust start collapsing due to overdensity, they come in and form a disk, and from that disk material falls into the central part and forms a star. The same thing happens in a galaxy. A collection of stars come like this, and so the disk is formed rather than the. That's why you see all systems basically in that form. Now, the older a galaxy gets, this changes, and you can see it form a more spherical type called elliptical galaxy.
Mhm.
This is when a lot of the stars have quit glowing as bright as they are and become older and everything. These elliptical galaxies contain very many old stars.
And I
But
just,
let me just say, that's a very, very interesting, good question. We don't fully understand how galaxies form yet. Like I said, we have the problem of already their formation much earlier than we ever expected it to be. So there's a lot to learn yet.
right. And how did you decide to become an astrophysicist to share with the audience before we wrap up?
Oh, by sheer accident. uh, my Ph.D. at MIT was done in elementary particle physics. So I was going to be an elementary particle physicist and work at accelerators. But my first job was at the University of Rochester in the physics department there. And I went there to study particle physics. But one day we were gathering together and someone said, "Oh, look at this article by Professor Philip Morrison at Cornell University. It says that this galaxy uh, out in space was a very, very strong source of radio waves. And it looked like two blobs together. So Professor Morrison proposed that this was a matter-antimatter galaxy in collision. And when those galaxies annihilate, they annihilate into large numbers of gamma rays. So being an elementary particle physicist, I knew how to make gamma ray detectors. So we said, we know how to make gamma ray detectors. We'll build one of these and go and look for this, and we'll easily detect it. We predicted what flux we should see. The problem was that the gamma rays are absorbed by the atmosphere, and so you have to put your gamma ray camera in a balloon and fly it up above the atmosphere. So we did that, and we saw nothing the first few flights that we had. And then I kept doing it for another 10 years and still didn't find anything. And it soon became obvious that you had to go into a satellite where you could get much larger observing times above the atmosphere. So I essentially gave that up and then moved into infrared astronomy and do that. So I became a astrophysicist completely by accident. To tell you, I'm not proud of this, but I've never had an astronomy course in my life.
I think you've had the time to have astronomy experience by doing, which is smart.
Yeah. I picked it up as I needed it, and sometimes it shows. My ignorance shows quite often, in fact.
But I like to think of ignorance as the path to continue learning. So it's not.
Oh yeah, no, you're right. That's a very good point. That's a very good point. Yeah. No, I've been blessed to have the career that I've had. Yeah.
Mm-hmm. I know you say on accident, but since speaking with you last week, I like to think that you became an astrophysicist on purpose.
No.
You chose a path.
I knew I wanted to be a nuclear physicist. Yeah. No, I made up my mind in the 8th grade what I wanted to be. And I had the catalogs for college and graduate school in the 8th grade. And really, why, I don't know. But I just, like an arrow, like I think I told you, just like an arrow, I just went and did college and graduate school in essential nuclear physics or elementary particle physics. And just by accident, I drifted over to astrophysics by looking for these gamma rays.
But how lucky we are as, just the community of learners and the astrophysicist community and astrophysics community, rather, how lucky are we that you stumbled upon it on that path,
Oh, yeah. Well, no, it's been a joy for me. I mean, I love it. I probably should have retired a long time ago, but I really love it. I love to do this work. It's just so exciting. Every day, you never know what's going to show up.
Mm-hmm. And just before we wrap up, one last question, just for context. Can you tell us about how the Spitzer telescope paved the way for the James Webb Space Telescope? To share it.
Oh, yes. Yeah. The Spitzer Space Telescope, which is one of NASA's great observatories, is an infrared telescope, just like Hubble. Just like James Webb, but it was just much, much smaller. That's all. Like I said, it was only 85 centimeters instead of 6.5 meters in size. Just one little small beryllium mirror. And it worked for 16 years. And we learned a lot, how to cool mirrors in space. In infrared, you need to cool the mirror because the mirror emits infrared radiation. And so we learned a lot of things of how to build an infrared telescope that James Webb has incorporated into it. And we scanned a lot of the sky, so we knew where the interesting places to look with the James Webb was identified. Yeah. Mm-hmm. And a prime example was that with Hubble, we looked back a certain amount of time. I keep confusing these. With Spitzer, we looked back, looking for the deepest galaxies, and we went much deeper than ever gone before. But then James Webb came along, and with a bigger mirror and more sensitive sectors, it went even further. Yeah. So.
Yeah. And Eric Olson had one follow-up question. Other than Webb seeing back further in time, due to the infrared detector versus the Hubble, what else have you seen that surprised you from the JWST?
Well, I've mostly been interested in these examples, but there's an awful lot in lots of fields in star formation, uncovering what's going on there, and looking for there's a lot of work being done on exoplanets, and particularly one of the interesting things is that by looking, James Webb has been able to look in the atmospheres of these exoplanets and then begin to find out whether there's organic molecules or evidence of life in it. And I think that's maybe where we're going to find some big advances.
Amazing. Well, Dr. Fazio, I just wanted to say thank you again so much for
Sure.
sharing all of your wonderful and impressive knowledge with us. It's been such an honor to host you
Well,
for the Science Speaker Series this evening.
Well,
Such a
thank you.
distinguished and accomplished presenter.
Well, thank you very much. I really appreciate your asking me, and I really enjoy doing this. Like I said, the people out there are paying for my research with your taxes, so I owe you something. Okay.
We appreciate that.
Okay.
So
Bye,
to-
Janelle.
By Dr. Fazio, and just wanted to say a thank you to our sponsors again, Bank of America, our lead sponsor, to White
Okay.
Elephant Hotels and Resorts, and Cisco Brewers of Nantucket, who make our Science Speaker Series complimentary and accessible to all of our viewers and our patrons. It is with the utmost respect and pleasure that I wish you all a good night and a good evening.
Okay.
Thank you so much.
Good night, everyone. Thank you for coming.